Okay, good morning, everyone. Yeah, thank you to Mark and his group Talks for organizing this really excellent conference so far, and thanks to all of you for the wonderful conversations over pints of Guinness and banjo music. We've been hearing a lot about what makes a good clock, the theory of timekeeping, the theory of time itself, how to think about time. But I'm going to sort of give you a bit of a more, useful, digestible question within the realm of theory. Anyway. So if I give you access to a clock of a given quality, what can we do with it within the context of quantum information? This is going to be sort of our modus operandi for this talk. And before I get started, I would just like to introduce myself a bit. So my name is Xuereb. I am originally from Malta, and I am doing a PhD in the TiQT group in Vienna. Those are all the people in the group right now. I do have an Irish connection, but so I spent sort of half of my master's here, and this is originally how I ended up learning about clocks and getting involved in this clocky business. And I'm sort of interested in two main things, sort of fundamental relationships between thermodynamics and information processing, and also using thermodynamics to derive limitations on what you can do in quantum information processing. And today's talk is sort of around that work, and this work is also done, thanks to some people which are here, like Mark and Flo and Pauli, and also my supervisor, Mark Xuereb. So what we will cover is loosely, so I will convince you that time is useful and important when thinking about computation. We'll go over some techniques that we need to be able to answer this question, and then we'll see some results related to what complexity of some circuit can you achieve with access to some clock, and also maybe can you cool a qubit if you have a bad clock. So let's see. And so to begin with, I think each of us, when we think of a quantum information process, there are three distinct sort of mindsets you can take, three different aesthetics, if you like. Like if you're a mathematician, you just think of a unitary and from SUN, and you just think of a rotation, and you don't really care what it is. If you're a computer scientist, maybe you say, I have this gate set, and I'm going to use this gate set to come up with some probability distribution, and I care that this probability distribution is PQP advantageous, and that's great. But then if you're a physicist, you care about shooting some laser pulse to address an energy splitting, and actually create this probability distribution through a physical process. And since the majority of us in this room are physicists, I'm going to ask you to indulge me to take this perspective on board a bit in the next 30 minutes. And so a computation, really, you can think of it like this. So you have some Hamiltonian, and you want to run this Hamiltonian for some time, tau, a specific time tau, e to the minus ih tau, a specific one. So you get a specific unitary. And notice that if you have some epsilon there, you get a different unitary. And I just want to flash this quote by Paris very quickly, that in this great paper, that the Hamiltonian approach to quantum physics carries with it the seeds of its own demise. And now Paris was trying to say many things here. I don't know, if you try to come up with an operator for time, it's unbounded, so try something else. If you try to come up with a quantum clock, use it for control. Controlling the other quantum system will degrade your clock. So you're failing too. But for us, really, it's this intuition that if we can't have an operator, then we have this parameter t, and we have to get it through some sort of quantum clock or classical clock process. Then if the clock isn't so good, you're going to get another unitary, and you have some error in your computation. So, a situation like this. So with Paris's quote in mind, how does this impact our ability to do quantum computation? This is our motivating question. And to understand that, we need to understand what it means to have a good clock. So how is it going to disturb us? Thankfully, my good friend Florian Meier has done a lot of work for me here, so I don't need to ramble on too much. But I can just remind you that for a ticking clock, you have some sort of frequency being generated. You discretize this frequency, so you do some counting, and this gives you some notion of a tick, some tau. And the accuracy of this clock is going to be this n term I will use to denote accuracy, is given by the mean. So the average tick time tau is if you're wanting to time a process for 5 seconds, this is going to be your tau. And sigma is the variance in this tick signal, okay? Of course, as well, now we've all learned about autonomous thermal clocks and these models, and there is also this nice upper bound, which is also related to TORs, that the entropy production per tick somehow upper bounds the clock accuracy. And this might also motivate us now to think, okay, if I need to pay some cost to have an accuracy of some clock, and the clock is important for the computation, maybe we can also follow this line of reasoning to say, the computation itself might have some entropy production we can relate to the clock. Okay, very good. So now, yes, we need to think about these mathematical objects. Okay, so these are these so-called tick distributions. Florian talked to us about them a bit, and they are these representations of what I was telling you about this mean and this variance. Okay, so basically, if you have a perfect clock, and we only care about the single tick, and for the sake of this talk, right? Because we want to time a unitary one, let's say. Then, if you're trying to do this time evolution going from rho naught to rho prime, and so you have these generators there giving you this time evolution, but now you consider this sort of statistically, like, okay, I'm trying to do this time evolution many times, how often am I doing it right? Implicitly, you kind of always assume that there's this kind of Dirac delta distribution, which is always giving you good temporal information. But clocks aren't perfect, unless you pay infinite entropy production. So let's say we turn this into a Gaussian now, what happens? So we can examine this kind of term by term in the energy eigenbasis of the Hamiltonian that's generating this time evolution, and it teaches us something quite nice. So if you expand this term by term, you will basically see that in the off-diagonal terms, you have the time evolution you expect by the generator, but also this dephasing term. And notice that this dephasing term is directly related to the variance of the tick distribution. Okay, so this is one way to see that imperfect timekeeping leads to dephasing over the unitary you're trying to generate. Another way to think of this, perhaps an easier way, is that if I'm trying to do this e to the IHT, and sometimes I'm getting t plus epsilon, t minus epsilon, then this is kind of like a mixed unitary channel, okay? Like I'm trying to get these different, this one unitary, but I'm getting the statistical mixing of other unitaries in there. This is a mixed unitary channel. Dephasing is a mixed unitary channel. So this is another way to think about how you get this type of impact on your computation. So you want this time evolution, this is the unitary you desire, but because of your imperfect clock, you're going to have to eat this dephasing in the energy eigenbasis of the Hamiltonian that generates your desired unitary. So now, okay, what can we do? So we can try to do some sort of state fidelity, so we can say, this is my desired state, sigma, maybe this is my bad state, rho, due to imperfect timekeeping, and this will give me a measure of how bad it is. But that's not that good. It gives you sort of a measure for a specific state. What can you do instead? Well, okay, dephasing is a channel, so we can put the channel around the time evolution and see what fidelity, how it impacts the fidelity. Okay, but that's only for a specific gate. So what can we do? Also, we can Haar average. So Haar averaging gives you a notion of how a single channel impacts sort of evolution over the whole Bloch sphere, okay? So it's this kind of geometric average over the Bloch sphere, and very sort of useful is Meier-Nielsen has this very nice formula for this quantity, which is simply related to the Krauss operators of the channel of interest. And we know that we have the phasing. We also know what the Krauss operators of the phasing look like. Before that, maybe, I can give some people here the word Haar measure all the time, but they don't always know what it is. So the Bloch sphere, if you like, do this Euclidean uniform distribution, you get sort of concentration around the poles. The Haar measure takes this into account and makes things nice. But yes, as I was saying, dephasing, we know the Krauss operators for a single qubit. So now we can do this baby first step calculation, okay? So these are the Krauss operators for single qubit dephasing, and we know what this dephasing rate is going to be from our prior calculation. It's going to be related to the energy difference in the spectrum of the Hamiltonian generating, this guy, and the variance in the tick distribution. And this gives you, you chuck these into the formula by Nielsen, and you get this nice formula. So, what does this teach you? It teaches you that the average gate fidelity is related directly to two quantities. The angle you're covering in the Bloch sphere, and also the clock accuracy. So, basically, the greater your angle in the Bloch sphere, the more you're going to be impacted by a bad clock, I think this is quite intuitive. And how bad the clock is can really limit, exponentially impact the fidelity you have access to. And you might say, why do you still have a 2/3? Well, even with the maximum mix state, you still have some fidelity, okay? So this should give you some idea for why there's a constant to which you approach, okay? And there is also some idea here around speed of computation when you consider this fraction. So like if you want to keep the same clock accuracy and you want to make tau smaller, you're going to eat more sigma. So going faster might not necessarily be a good idea. So that's what we learned here. But maybe we want to be more, more adventurous, more theoretically adventurous. Maybe we want to impress some referees. I don't know. So maybe you want to come up with a more general result. Okay, so we have the single qubit result, which gave us some intuition. But now we want to ask the question, okay, what about in a generic circuit? What happens? So I can perhaps first give you the setting for the result, and then I'll maybe explain to you a bit the intuition behind the result. So the result tells you, I have this kind of circuit, and we're going to care about CNOTs here for the sake of gate complexity. In general, this result stands for any really Clifford circuit. So if you have like identity X, Y, Z, and CNOT, this result holds because it's around a property of the Pauli's. But basically, let's say you pick this gate that you're going to care about, the CNOTs. And now, within a given time step, we're going to say, I'm going to make sure that these gates do not intersect, so they're going to be parallel within a given time step. And I'm going to say there's going to be LT of them in a given time step. And each is going to be controlled by an IID clock with a Gaussian tick distribution. And of course, it has the same mean because it's the same operation, because we're caring about one. And now, within time steps, you can have different gate arrangements that will intersect and hit each other. And each step is as well a dephasing channel because each one is coming from these clocks. So okay, this is the setup, and we want to ask, what's the average gate fidelity at the end of a big circuit, depending on its size, how many gates do I have, and how good is my clock? And it turns out you can upper bound this average gate fidelity in the following way, where L is the total number of gates in your circuit, and N is the clock accuracy. You're seeing a pi there because it's the time you need to do a C. Okay, but how do you actually get this result, no? We can go through it step by step. I don't think it's too hard, and I'm good on time, so indulge me. So each gate is dephased by two cross operators, okay? And so, like if you take this step, we have two gates. So we're going to have a tensor product of these guys, namely having 4 cross operators in each, like in such a time step. So in particular, if you have LT gates, you're going to have 2 to the LT terms in this tensor product of these guys. Okay, so this is somehow a big dephasing channel. They're independent dephasing of each gate. Good. So one time step is a tensor product of independent dephasing channels. What's happening in M time step? Well, you concatenate M of those big independent dephasing channels, and now our goal should be to bound that concatenation. And that's a very scary task because you already have these 2 to the LT cross operators. Now you're multiplying them M times in this concatenation. It's actually a direct product. So you have 2 to the LT terms exponentiated by M. Very scary. But if you keep in mind the structure of dephasing, you have this guy which is the identity, and this which will introduce this dephasing noise. But we assumed our clock is not horrible, right? So really and truly, this is mostly going to be a channel which is close to the identity in most cases. And in those cases, there exists this nice upper bound on the average gate fidelity, which is by this term called the unitarity. So unitarity is a measure of how much a channel disturbs how unitary a channel is, like how much it squashes the block sphere, really. And the nice thing here is that the unitarity is given by a 2 norm of the Krauss operators. And this 2 norm now, we can be quite happy that we have a 2 norm, because I told you that we're going to use Pauli's here, And Paulis are involuntary, which means when a Pauli hits a Pauli, and if you have Pauli I times Pauli j, you're still in a Pauli, right? So they're a group. And they're involuntary, which means when a Pauli hits a Pauli, you get an identity. And so now what we care about is actually these binomial contributions like this. And we do some maths, we see that the unitarity is this term, we plug it into this upper bound, and we get the nice result. So that's how you prove this thing. I don't think it's, too bad. And it gives you a fairly nice result that, allows you to smile at your theorist friends and not be afraid of them. No? Okay, so that's how we prove this. What's the experimental implications? What does it mean? Okay. Maybe even next slide. Okay. So this is a temperature plot of this upper bound, and this is the background temperature plot is for 1 C0 per time step. So if you're trying to do 1 C0 per time step, then a clock accuracy of like 1 times 10 to the 6 will give you access to 100,000 C0s, like in a row. Cool. But then you see, like if you're here, you're already hitting these like 0.5 fidelities at the end of your computation, which is basically, you could have put some sand in a box and shook it out, and it's a same output. And here, and of course, I should say, these astronomical numbers of C0s are not things which are unreal. Like if you look at these benchmarking algorithms, there are people that expect that they should be able to do 25,000 C0s. Talk to your favorite variational quantum algorithm friend. He will tell you he wants significant depth. And so then we can also apply the bound where we can set the number of C0s we want per time step, and this is what is happening in this inset C. So basically, the more C0s you want per time step, the more clock accuracy you need to reach a different depth, right? And now you can say, okay, I'm an ion trapper, Jake, I want to understand what this means. So what this means is that for this fidelity threshold of 0.5, which we agree is sort of like when it becomes garbage, so I get garbage after like 1 million C0s, maybe I'm okay. That would mean I need a clock accuracy of 1 million. And if you think of a pulse of 100 nanoseconds, this would mean that you need access to a clock accuracy of 0.1 nanoseconds, and the Arctic Sonara, which is this trapped ion controlled object, which I know nothing about, but I know it has a jitter of 0.3. So this is not like unrealistic, okay? These are numbers we can go back to our trapped ion friends and talk to. The issue is that there are many types of experimental error which can be thought of as timekeeping error. And this is a challenge which we need to meet as theorists. We need to go and talk to experimental people and understand what these timekeeping errors are, to characterize them so we can come up with better error mitigating strategies. So the second result, and I think the last result I will leave you with, is can you cool a qubit with access to a bad clock? And so this was kind of, I like quantum thermodynamics, I'm in a quantum thermo group, and I think we wanted to, wanted to sneak some thermo into the paper, basically. And what does it mean to cool a qubit for those that are not quantum thermo familiar? So in this sort of framework of thermal machines, what happens is that, a qubit, you have 2 energy levels, right? So like your populations. And if all your populations are in the 0 state, then you can, and your Hamiltonian is sigma z, basically what that would mean is that you're at beta equals minus infinity. So you're like 0 temperature is related to the 0 state, like the computational 0 state. The maximum mixed state, on the other hand, is at infinite temperature, because these populations are like this, and if you write it out as a thermal state of sigma z, it would mean that you're at infinite temperature. So it's a game of populations. And there is this nice gate, known as the swap gate, which allows you to swap populations. So we can now do this sort of thermodynamic game of swapping populations. And thermal machines, what they are is really, you say I have access to some like qubit with some population distribution, and I'm going to swap with it at every time step. Now, if I had access to a thermal machine with the specific populations I desire, I could cool to it through a single swap in one time step. So what's imperfect timekeeping going to my swap? Well, it dephases the swap, and what that means is that you end up with a partial swap. So like, if you have your machine here, and I'm trying to get all of this population I desire, I'm only able to get half of it, a third of it, at worst, almost nothing of it. And depending on the clock accuracy you have access to. So the worse the clock accuracy is, the less population you're able to grab in a given time step. But you can see where this argument is going. Asymptotically, you can always reach this temperature, with the proviso that your thermal machine is allowed to refresh within a given time step. So if I can always swap a bit with my desired thermal machine, my desired sort of virtual qubit subspace of the thermal machine, then asymptotically I reach the temperature. And that's kind of how that proof works. So there are some there are some tasks which you can even do with like an arbitrarily terrible clock, like cooling a qubit, as long as you're willing to wait, as long as you want. But then for generic tasks, tasks of arbitrary circuit complexity and so on, a clock is a real limiting factor, and we should think about this. So to summarize, listen to pairs, be afraid of your unitaries, they're not real, they're just platonic forms. Experimentalists, let's measure sigma. I'd love to talk about this. Achieving better timekeeping means more entropy production or slower gates. And better timekeeping means you get higher gate complexities. And there are some things you can achieve even with a perfect clock, like algorithmically cooling a qubit. So with that, thank you.
Presentation of how clock technology is going to ultimately limit our ability to do quantum computing in the circuit-based architecture. But that's not the only way to do quantum computing. There are these other methods like the coherent easy machine, which are based on bifurcations and on the steady states, and of course annealing-type dynamic quantum computing. Have you thought about what the thermodynamic constraints on those machines would be? Are they just as difficult as the circuit-based case?
Indeed, a very good question, and one that we are definitely motivated in trying to answer and develop other computing formalisms where the clock is at the heart of it, not just this classical sort of oracle which gives you this time information. Like if you truly incorporate your timekeeping device as part of your computation register itself, you might see spatial advantages, right? Because now if everything is quantum, maybe you can really fit it into a box. But also now you are able to use sort of these coherent operations between the clock and the computation register itself. But this might run you into the trouble of entangling the clock and the computation register. So there are also things to worry about. It would also allow us to talk about the thermodynamics of the computation and the clock itself in a nicer language, because now sort of everything has Hamiltonians of similar energies, more or less, like the clock and the computation itself. But we are still early in the game here, so all I can say is we're very, you're right to point out that this is something that we should think about, and we are definitely trying to do this, and maybe at the next TiQT we can hear more about that.
Okay.
If you want to I'm sure everyone wants, is hungry for biscuits.
Thanks for the very good talk. So I was wondering, when you were using the cross, so you were using a specific cross operator, but they are not unique. So is it an invariant, I guess?
That's a very good point, because all cross decompositions are non-unique, and without isometry will they change? I would hope not, in the sense that it would still have to have the same outcome, right? Like even if you have the same, sort of, if you have this big map, okay, this big map can be related to different cross decompositions, but like ultimately, when I apply it on row, I have to get the same output, right? So, and in some sense, what we quantify is the impact of the output. Like, so I do think that it's a cross-operator independent statement, but also the decomposition into like Pauli's is I think also very standard. So, but if you have other ideas for different cross decompositions, I would be happy to discuss them. So.
Well, yeah, maybe I can. Just before, when you touched upon the fact that there might be actually different clocks with different accuracies impacting your gauge efficiency, I was just wondering if you could say a little bit more about that and like how different accuracies of clock can actually interplay impacting the gauge.
Yes. So this really came about because, okay, we got this bound, and then you're like, what does this mean, right? So we emailed the track line people at this book, and we were like, okay, we have this bound, what does this mean? And I wanted to know what sigma to put into my bound to see that it makes sense, basically. And they were telling me, look, I mean, there's a lot of different timekeeping errors, you know, like this Arctic Sonara gives you this like controlled signal, right? Like sort of turn on laser now, turn it off now. And it has this sort of error of plus or minus 0.2 nanoseconds because of literal electric jitter in the signal. But then on top of that, for example, like these pulse sequences, sort of the pulse shape itself, because of other timekeeping noise can broaden, for example. That's another type of error which they told me about, but I don't know how to quantify. And I'm sure there are others that I can't think of. And basically, you know, this Arctic Sonara has a time card, and the time card has this value. But like, if you actually try to model the timekeeping, what's going on there? And there are a bunch. I think Michael spoke about the superconducting clock experiment in Queensland by Arkady Fedorov. And they really try to keep track of a lot of these timekeeping errors. So I think that's a really good reference to try to look into this. But basically what I'd say is it would be really great if experimentalists would start trying to keep track of things like a tick distribution. You know, because then as theorists we can really do something with that. But at the same time, I understand it's a challenge for them to sort of really categorize errors. And like when you see these like error tables in these papers that just have 9 errors, probably in truth they have actually like 200 that they just don't want to tell you how or something, or are very, very small. So I don't know, I think we just need to have better dialogue between theorists and experimentalists. And it's up to us, like, for example, this work on like how dephasing error grows in a circuit. Like, of course there's been other work in the past on like how error grows throughout random circuits, but relating error to its physical origins is, I think, a very important thing, because then we can talk to experimentalists. So I think the motivation should be on both ends to sort of try to talk to each other, and I think that was one of the things that we tried to do.
I mean, in principle, we have time for one more quick question, but I think everyone seems happy with it, so we can start 3 minutes earlier.